Welcome back to the deep dive. Today, we are going to challenge a pretty massive, almost instinctive assumption in the tech world.
Yeah, it's a big one.
Right. So, you know how in the fast-moving world of AI, everyone is totally obsessed with the next big thing. It feels like, I don't know, every week there's a paper claiming they've invented a radically new architecture or like a completely new way for a machine to think.
It is entirely the nature of the field. We have this massive bias toward novelty. We tend to just assume that newer is automatically better
Right, right.
and that complexity equals progress. If a model has a more complicated diagram in the paper, we kind of assume it must be smarter.
Exactly. But here is the hook for today's dive, for you listening. What if the previous breakthrough wasn't actually flawed? What if it was just undercooked?
Undercooked is the perfect word. That is the central question of the source material we're covering today. It suggests we might be way too quick to throw out the recipe when we really should just be, leaving the cake in the oven a little longer.
Turning up the heat.
Right, maybe turn up the heat, maybe use better flour.
So today we are diving into a paper titled RoBERTa, a robustly optimized BERT pre-training approach.
Right.
And this comes from a really heavyweight team over at Facebook AI and the University of Washington, researchers like Yinhan Liu, Mile Ott, and their colleagues.
And frankly, this paper is a masterclass in scientific rigor,
Mm-hmm.
which I know that sounds a bit dry, but hear me out.
I'm listening.
It is technically a replication study of BERT, which usually sounds incredibly boring. We did the same thing again. Isn't exactly a headline that sets the AI world on fire.
Yeah, nobody wants to read "We did it again."
Exactly. But their replication ended up beating the state-of-the-art models of the time, models that explicitly claimed to be far superior to BERT purely because of their complex, novel designs.
Which is wild,
Yeah.
because they didn't invent a new brain for the AI. They just took the existing brain BERT and essentially sent it to a much better gym.
Precisely. They wanted to evaluate the effects of hyperparameter tuning and training set size. They essentially asked the community, did we really hit the limit of what BERT can do, or did the original researchers just sort of stop training it too soon?
Okay, before we get into the how, let's set the scene briefly for you. We have BERT. BERT was the big cheese, the absolute standard everyone was trying to beat in natural language processing.
Right. BERT, which stands for Bidirectional Encoder Representations from Transformers, when it dropped, it changed everything. But very quickly, these post-BERT models started popping up everywhere. The most prominent rival at the time was a model called XLNet.
And XLNet claimed it was better because it had a smarter architecture, right? It wasn't
Right.
just a copy. They actually changed the fundamental math of how it processed language.
That was the claim, yeah. They argued that BERT had fundamental limitations in how it handled masking and prediction. But the authors of the RoBERTa paper, they looked at these comparisons and noticed a pretty glaring problem in the scientific process. Comparing these models is actually incredibly hard.
Why is it so hard, though? If Model A scores higher than Model B on a standardized test, isn't Model A just better?
Well, not necessarily, because in AI research, you rarely have a true apples-to-apples comparison. Everyone uses entirely different data sets.
Right.
Everyone trains for different amounts of time using completely different hardware setups. If I train my model on, the entire internet for a month, and you train yours on a stack of encyclopedias for a RIC, my model will probably win the test.
Sure.
But that doesn't mean my architecture is inherently better. It just means my resources were better.
So the game is rigged if you don't aggressively control the variables.
Exactly. The RoBERTa team hypothesized that BERT was significantly undertrained. They genuinely believed that if they leveled the playing field, gave it the same data, rigorous tuning BERT could still compete with, or even utterly crush, the newer, fancier models like XLNet.
So their mission was basically to push BERT to its absolute physical limit, hence the name, right?
Yeah.
Robustly optimized BERT approach, RoBERTa.
That's the one.
Let's look at how they actually did that. It seems like the first major change was just volume. We are talking about a massive, massive jump in the amount of data they fed this thing.
The difference is staggering. To give you some context, the original BERT was trained on about 16 gigabytes of uncompressed text. That consisted mostly of the book corpus and the English Wikipedia.
16 gigabytes.
Yeah.
Which, for a human is a lifetime of reading, but for an AI?
It's just a light snack.
Right, a warm-up. So RoBERTa scales this up.
Hugely. RoBERTa was trained on over 160 gigabytes of uncompressed text.
10 times the data. That is a massive scale-up.
Yes. But I want to be very clear here. It wasn't just about dumping a random text dump into the system. They were very specific about the quality and the diversity of that data. They didn't just scrape random internet junk.
I was looking at the source list for the data, and it is totally fascinating, where they went to find 160 gigabytes of high-quality English text. One of the big chunks was something they actually collected themselves called CC New Ws.
Right. This was a novel data set they put together specifically for this project. It contains 63 million English news articles crawled between 2016 and 2019. That alone was about 76 gigabytes.
Why focus so heavily on news?
Because the original BERT relied heavily on Wikipedia, and Wikipedia is great, but it's encyclopedic, it's static. News articles capture the flow of current events, how language is actually evolving in real time, and they cover a much wider array of topics than an encyclopedia might normally feature. It gives the model a very current, factual understanding of the world.
That makes a lot of sense. But then they also use something called open web text. And I absolutely love this detail. It's web content extracted from URLs shared on Reddit. But not just any URLs. They had to have at least 3 upvotes.
It sounds funny, I know, but it is an incredibly clever heuristic for quality control.
It really is.
The internet is full of spam, auto-generated text, and just pure incoherence. If a link on Reddit has at least 3 upvotes, it implies a real human actually looked at it, read it, and found it interesting or relevant. It naturally filters out the noise. That contributed another 38 gigabytes of human-verified content.
The internet-approved filter. If 3 people on Reddit liked it, it's probably legible English.
Essentially, yes. It's a proxy for quality. And finally, they used a data set called stories.
Which is exactly what it sounds like.
Pretty much. This is a subset of Common Crawl that is specifically filtered to match a story-like style. This is crucial because news articles and Wikipedia are very factual and dry. The stories dataset helps the model understand narrative structures, dialogue, and flow, which is essential for more creative tasks or understanding fiction.
So what does all this tell us when we connect this to the bigger picture of AI development?
It demonstrates that simply feeding the model more diverse, high-quality text yields drastically better downstream performance. You don't necessarily need to change the model's brain structure. You just need to give it a richer education. The original BERT simply hadn't seen enough of the world yet.
Like a sheltered kid.
Right. It's the difference between a student who only reads textbooks and a student who reads textbooks, newspapers, novels, and debate forums. The second student is going to be much more robust in their thinking.
Hence the name.
Yeah.
Robustly optimized. Okay, so they have better ingredients. Now let's talk about the recipe itself, the actual training procedure. One of the technical tweaks they made involves something called masked language modeling. Can you break that down for us without getting too deep into the math?
Sure. This is the absolute core of how BERT learns. Imagine I give you a sentence, but I cover up one of the words with a piece of tape. Your job is to guess what the hidden word is based on the context of the other words around it.
Like a fill-in-the-blank test. The quick brown fox blank over the lazy dog.
Exactly. The model learns language by trying to predict that the blank is jumps. Now, the original BERT used what we call static masking.
Static meaning the blanks didn't change.
Correct. They performed the masking once during the initial data pre-processing. So they would take a sentence, decide which words to hide, and save that specific version to the hard drive. Every single time the model saw that sentence during training, it saw the exact same words hidden.
Oh, I see the problem there. That's like taking a test, getting it wrong, studying, and then taking the exact same test again with the exact same questions blanked out. Eventually, you aren't really learning the language. You're just memorizing the answers for that specific flashcard.
That is a very fair way to put it. To mitigate this, the original BERT duplicated the data 10 times so they could have 10 different masks. But they trained for 40 epochs. So mathematically, the model would still see the exact same mask 4 times during its training cycle. It's inefficient, and it's highly prone to overfitting.
And RoBERTa?
RoBERTa uses dynamic masking. They generate a unique masking pattern every single time a sequence is fed to the model.
So the teacher changes which answers are blanked out every single time you retake the test.
Yes. This forces the model to actually learn the underlying relationships in the language rather than just relying on rote memory. The paper found that dynamic masking is comparable to or slightly better than static masking in terms of raw accuracy, but crucially, it is infinitely more efficient for training on massive data sets.
Because you don't have to save 10 versions of everything.
Exactly. You don't have to store 10 copies of your data just to change the masks. You save massive amounts of storage and you get better learning.
That makes total sense. Now, here is where it gets really interesting to me. They started busting some pretty big myths, specifically the myth of the next sentence prediction. This was a really big part of the original BERT, wasn't it?
It was. The original BERT had two distinct jobs. One was the fill-in-the-blank game we just discussed. The second job was next sentence prediction, or NSP. The model is given two sentences and basically has to guess do these belong together. Does sentence B logically follow sentence A?
And the logic was that this teaches the model about paragraph structure and overall logic.
Exactly. The original BERT paper explicitly claimed that removing this task hurt performance. They really thought it was essential for downstream tasks like question answering, where understanding the relationship between multiple sentences is key.
But the RoBERTa team said, are you sure about that?
They strongly questioned it. And this is where that rigorous testing comes in. They ran a series of experiments testing completely different input formats. They tested the original method, but they also tested feeding the model single natural sentences, and they tested packing full sentences together until they hit the maximum length of the model's memory.
And what did they actually find?
Well, first, they found that using individual sentences, just sentence A, then sentence B, actually hurts performance. The model desperately needs long contexts to learn long-range dependencies. If you only feed it short little snippets, it gets nearsighted.
Okay, so length matters. You need a block of text, not just a line.
But here's the twist. When they used full sentences, or doc sentences, which is essentially giving the model long, contiguous blocks of text up to 512 tokens, and removed the next sentence prediction task entirely, performance actually improved.
Wait, so the thing that BERT's creators thought was structurally essential was actually holding it back?
It appears so. The prevailing theory is that the NSP task was actually forcing the model to look at artificial breaks. By trying to guess if two specific sentences were connected, they were chopping up the data in a way that actively prevented the model from learning those really long-range connections across a whole paragraph or a whole document.
That is a classic case of addition by subtraction.
Yeah.
Stop trying to force it to play a guessing game about the next sentence, and just let the poor thing read the whole paragraph.
Exactly. It simplifies the training objective significantly. You just have the model read long, continuous streams of text. It turns out, if you read enough text, you figure out sentence relationships anyway. You don't need a special secondary game to teach it.
Okay, let's move over to the optimization section. This is usually the part where people's eyes glaze over batch sizes and encoding formats. But in this specific paper, it seems like these boring details were literally the secret sauce.
They absolutely were. Let's talk about batch size. The original BERT used a batch size of 256 sequences. RoBERTa cranked that up to 8,000 sequences.
That is a massive jump. Why does that actually matter? Is it just about going faster?
Speed is definitely a part of it.
Yep.
Large batches are much easier to parallelize on massive GPU clusters. But there is a very real mathematical benefit too. Think about gradients. When the model trains, it looks at a batch of data, sees where it made mistakes, and adjusts its internal dials.
Right.
If your batch is small, say just 256 items, the adjustment might be a bit jerky. Maybe that specific batch was just weird. The signal is noisy. But if your batch is 8,000 items, you are getting a much, much better average of what the correct overall adjustment should be.
Oh, I see.
The paper shows that increasing the batch size improved the model's perplexity. Basically, the model was less confused, and it was much more accurate on end tasks.
It's like polling. If you ask 10 people who they are voting for, your margin of error is huge. If you ask 10,000 people, your prediction is solid.
That's a perfect analogy. Larger batches give you a much cleaner signal for optimization. It makes the entire training process smoother and a lot more reliable.
And then there's the text encoding. They switched to something called byte-level BPE. We don't need to get bogged down in the deep math, but what is the practical difference for you as a user?
The original BERT used a character-level vocabulary of about 30,000 words or subwords. It had to do a lot of complex preprocessing. If it saw a weird character or a totally rare word it didn't know, it might struggle or have to use an unknown token.
The dreaded unknown token. I imagine that's incredibly frustrating for a model that's trying to read the Wild West of the internet.
It really is, especially with 160 gigabytes of web data. You have emojis, you have weird Unicode characters, complex scientific notation, typos everywhere.
So how does byte-level BPE fix that mess?
RoBERTa uses bytes, the raw digital information itself, as the base unit. It has a vocabulary of 50,000 bytes. The benefit is that it is a truly universal encoding scheme. It can encode any input text.
Anything.
Anything. It doesn't matter if it's a Japanese character, a smiley face, or a completely new slang word that was invented yesterday. It breaks it down into bytes. It never has to say, I don't know what this is.
So it's way more flexible. It's almost future-proofed against the weirdness of the internet.
Yeah, correct. And when you were dealing with the sheer scale of data they used, robustness to weirdness is an actual performance feature. It stops the model from constantly tripping over things it simply hasn't seen before.
Okay, so we have the new recipe. 160 gigabytes of diverse data, dynamic masking to stop it from memorizing the test, removing the next sentence prediction task, huge batch sizes for stability, and universal byte encoding. So, did the cake actually taste better? Let's talk results.
This is where RoBERTa really shines. They entirely reclaimed the crown. They tested it on all the major benchmarks: GLUE, Squad, and Race.
Let's start with GLUE. That's the General Language Understanding Evaluation. It's basically the decathlon for AI models.
Right. RoBERTa achieves state-of-the-art results on all 9 tasks in the GLUE development set, and on the public leaderboard, it matched or beat XLNet.
And remember, XLNet was the shiny new architecture that was supposed to be mathematically superior.
Exactly. RoBERTa set new high scores on tasks like MNLI, multi-genre natural language inference, and RTE, which is recognizing textual entailment. These are very hard tasks. They require genuine logic and nuance. It proves that the simple BERT architecture was fully capable of this reasoning all along. It just desperately needed better training.
What about Squad? That's the question-answering one.
On Squad version 2.0, which is particularly tricky because it includes unanswerable questions. Questions where the model actively has to realize the answer isn't in the text provided. RoBERTa set a new state-of-the-art. And it did this without using additional external training data for the fine-tuning stage, which previous winners all had to use.
So it's just smarter right out of the box.
Yep. And finally, Race. This is a dataset pulled from Chinese middle and high school English exams.
Why is that a benchmark? That sounds surprisingly specific.
It does, but those exams are notoriously difficult. They involve very long passages and require deep, complex reasoning. It's not just a find the keyword exercise. You have to understand the true intent of the author. You have to make inferences between the lines. RoBERTa achieved state-of-the-art results here as well.
I just love the irony of this so much. By training the old model correctly, just treating it right, giving it more time, more data, they beat all the models that were confidently claiming the old architecture was completely obsolete.
It is a really powerful lesson for the industry. The paper states RoBERTa provides a large improvement over the originally reported BERT large results, reaffirming the importance of the design choices we explored.
So let's wrap this up. What are the key takeaways for someone listening today? If you are building AI or just trying to understand it, what does RoBERTa teach us?
I think there are 4 main technical pillars to walk away with. 1, dynamic masking works much better for large data sets because you don't repeat the same easy questions. 2, you don't need next sentence prediction. You just need long, full sentences to learn true context. 3, train with huge batches for cleaner gradients. And 4, use byte-level encoding to handle any text without crashing on unknown symbols.
And from a bigger picture perspective,
The real so what here is that masked language model pre-training, the classic BERT style, is still incredibly competitive. We shouldn't rush to abandon simple architectures before we have fully explored their absolute limits. It raises a very important question for the field. How many other outdated models are sitting on shelves right now that are just one genuinely good training run away from being state-of-the-art?
that is such a great point. We get so obsessed with the model code that we completely forget the training code is half the battle.
Rigor matters. Hyperparameters matter. The meticulous details of how you train are often just as important as what you are training.
I have one question left in my mind. RoBERTa showed that 160 gigabytes of text and 500,000 training steps made a massive difference compared to the original BERT.
Yes.
So where is the ceiling? If 160 gigabytes did this, what happens at 1 terabyte or 10 terabytes? At what point does adding more data just stop helping?
That is the trillion-dollar question right now. The authors even note in the paper that their longest trained model didn't seem to overfit. It strongly implies they could have just kept going. We might still be nowhere near the limit of what these simple architectures can do if we just keep feeding them more of the internet.
A thought to keep you up at night. The cake might be delicious right now, but maybe it could be even better if we just left it in the oven for another week.
There is only one way to find out.
Thanks for listening to this deep dive into RoBERTa. Remember, sometimes the old ways really are the best ways, provided you optimize them robustly. Keep optimizing, and we'll see you next time.